how is the look like? Is it? It's not readable so much. Do you think it's readable? Or is it?
I think it's readable.
Readable?
Yes. It's basically like
Or does anybody? I think iPhone is better, I guess. Gets better. I think next time I should use iPhone or iPad, but I don't have iPad folder. I have iPad. Okay, hopefully it's okay. So can you start recording?
Yes, I already started writing.
Oh, it started writing.
Yeah.
Okay. Okay, let's get started. Wow, wonderful. Prepare. So welcome to the Differential Geometry and Topology and Physics course. I'm Satoshi Namata. So teaching assistant is you can call me Satoshi instead of saying whatever. Don't call me Laoshi or something. You can just call me Satoshi. I mean, it's okay. I mean, for you guys to call me Satoshi. Don't call me like a professor, Laoshi, sir. It's too formal. So the TA is here, Jack Yan. So my office is Jamwan at the S422. And then, so the plan is I will give you homework every week, and then you need to submit a week after. And then, yeah, so I need to tell you so the final grade is determined 80% of homework grade, and also 20% of final grade. So almost all the grade is determined by homework. And then, so deadline, after deadline, I will submit the solution. So let's see, after due date, the only 80% counts to of your homework counts to the final the grade. And after solution set, solution is set, it's only 50% of your grade. Will be counted. Do you understand what I mean? So after 1 week is the due date. 1 week after its due date, if you can spend more time if you want, but only 80%. But after solution is sent, you can just copy and paste all the solution. Still 30% matter of your grade. Okay, and then you can get the grade. Anyway, so for me, I don't care so much about the grading, and so I just want you to learn. So that's the rule. And oh my goodness, there are many students. How many of you guys from physics department? And how many of you from math department? Okay, 3 students. That's good enough. Okay. So my course is is designed for physics students, but whereas I think math students can learn something out of my course even. There are lots of interaction in geometry and physics, geometry and topology and physics recently, and then learning differential geometry and topology is indispensable to study physics recently. So, and also, it's better to learn how the language of mathematics instead of reading just you guys are getting used to the reading the physics book, but the math book is written in different style. So it's better to get used to read the even mathematics book. But in this course, I'm not going to give you a proof, but I just give you the meaning of the theorem and so on, and how to use them, and how the theorem is used in physics. that's the idea of my lectures. Okay, and then yeah. So about the office hour, so Fuda asked me to come to every week to Handan, but it's kind of troublesome to come here every week. So I would create a WeChat group, or he will create WeChat group, and you can join. And if you have a question, you can ask the WeChat group first, or you can email me. Okay? And then if you still not, if you cannot understand, you can we can meet in person. That's the role. And I'm in Jiangwan, so if you're a graduate student, it's that you can easily come to Jiangwan, so you can stop by my office anytime. Um, but it's better to ask questions in WeChat or email first. Um, okay, so that's the role of office. Okay. So let's get started. Um, so today I'm going to talk about a bit introduction. So introduction was some pro. Yeah. So and then I have my lecture note, which is you can see e-learning. Um, and if you want to audit my class, I can put you into the e-learning. So just tell me if you want to audit my class without registering, and I can put you to e-learning so that you can see the lecture note. So my so the so you can take a look at my lecture note on the e-learning. I will continuously update. So I just give you the first, 5 or 6 lecture, note for 5 or 6 lectures already. I have taught this course twice, but I will change the content of the note. So you can just take a look at the updated note. Cool. Any question? Okay. So, introduction for notes. So first I want to talk about the basic so-called topological inference called the order characteristic. So for instance, you just consider some so you're familiar with the so-called sphere, two-dimensional sphere, which is defined inside R3, defined by x squared plus y squared plus z squared is equal to say 1. Okay? This is called two-sphere. Yeah. So it's better. So basically I follow the note on the e-learning, but I will often draw the picture. So you can print out the lecture note and then put what I have written. No need to write down everything. Okay. No need to write down. It's a 2.5-hour lecture. So no need to write down all what I have what I write on the blackboard. But sometimes I will write something not written here, or I would draw lots of pictures. So it's better to print out and put something, some remark or something on the margin. That's how you can learn from in my lecture. So this is two-sphere, but a lot of surface in two-dimensional. For instance, so people just have it's called Taurus. People just E2, and usually you have lots of hole. So this is two-dimensional surface, real two-dimensional surface, and this the study of two-dimensional surface dates back to the early 19th century due to Gauss. Even before Gauss, the basic notion, so-called topological inference, first introduced by Euler. For instance, so this sphere can be approximated as follows. For instance, it's not the same thing, but you can push, how to say, you can start from tetrahedron, and you can just put the air inside, then it becomes the sphere, right? So a sphere. And similarly, you can have a lot of tetrahedron, and then hexahedron, and also one can have lots of things. All this picture, if you put the air inside, it becomes a sphere. If it is made of rubber or something. And for instance, one can count vertex, edge, and the faces. Let's count vertex, edge, faces. So vertex is, let's see, 1, 2, 3, 4. Vertex is 4. And the edges is 1, 2, 3, 4, 5, 6. How many faces? 1, 2, 3, and 4. 4. And what you need to do is b minus e plus f is equal to 2. Okay. So let's do a similar thing for this one. Hexahedron. So you have how many vertex? 8. Just speak out. 8. How many edges? 12. Okay. Faster than I am. Okay. How many faces? 6. Okay. Okay. Do the similar exercise. What you get is 8 minus 12 plus 6 is 2. Okay. So let's do the next exercise. So how many vertex? 6. How many edges? 6 to 12. Is it 12? And how many faces? 8. Good. 8. And in total it's 2. So how many way, whatever way you can approximate this sphere by so-called, this is called cell decomposition. It's called cell. So this is called 0 cell, this is 1 cell, and 2 cell, and so on. This is called. How many way? However you approximate a sphere by cell decomposition, at the end of the day, b minus e plus f is equal to 2. Okay? So this is called, this number is called Euler characteristic. Euler characteristic. So this quantity is called Euler characteristic. It's the most basic topological invariant, but most important one, okay? Which is introduced by Euler. But the two, how to say? So this is two-dimensional surface. So let's do the following. The next exercise, this one, okay? Torus. So torus can be obtained by identify two edges, two edges up and down, and the left hand. So if you identify the, how to say, start with rectangle and identify bottom and upper edges, what you get is the cylinder. Okay. And if you identify left edges and right edges, what you will get is torus. Okay, you can just glue them. You get torus. And how many edges does it have? This cell decomposition. What's B? 1. What? 1. Good. So this point is identify this point. Okay. Because you just identify top and bottom. And this edges identify this edges. So these points are the same point, which means the cell decomposition is, you think curvature? Oh no, there is no curvature. There is one. So this edge corresponds to, I think it's better to use this. And then this edge corresponds to, and this vertex is this point, okay? And how many edges does it have? 1, 2, and how many faces? 1, right? And what's our characteristic? 0. So our characteristic is 0. So it's a different from the sphere case, self-decomposition. So they're distinguished, but they're different as a topology. They have a different topology. That's so you cannot continuously move from one to the other. That's how the topology can divide and distinguish the surface. So another way to obtain the order characteristic is so-called, you just introduce so-called vector field on the surface. So vector field. So vector field is the, I'm sure you're so familiar with vector field. For instance, if you have a charges electron at origin, and then you just consider vector field or electric. So electric field E. So for instance, P which is E is proportional to 1 over R squared, right? Just omit the constant, and then people just write down the vector field like this way. Around this point, the length is around this sphere. Length is like this way. If you go to the radius is bigger, it's the arrow becomes shorter, okay? Because of 1 over R squared, okay? It's proportional. The length is 1 over R squared. That's called vector field, okay? Electric vector field. People just vector field. So, for instance, if you consider the vector field of sphere, let's consider vector field sphere. So vector field sphere, the one way is to define how vector field sphere is as follows. You just consider it's called gradient vector field on height function in mathematical language, but you just go. There's a function, height function. Okay? You just map the point on the sphere to the R. Okay? It becomes a point. So you just measure the height of the point, okay, on this z-axis. And then you can just consider vector field, which is differential of this function. So that starts from south pole, okay? South pole, and the vector field starts with, let's see, and it goes to north pole. So for instance, the vector field can be written like this way. Let's see. So, and you just look at the north pole and south pole, how the vector field look like. So, south pole And you just look at the neighborhood of the South Pole around this place and the North Pole. And then South Pole, there's a South Pole here. And then the vector field starts with 0 is here, and then it becomes like this. At the end of the day, it's around the, let's see, around the circle, the vector field is like, becomes like this way. Okay. Then, so you just consider the vector field as you rotate the vector field around the South Pole on the 2 pi, 360 degrees. The vector field itself rotates 360. Okay. So therefore, how many times it rounds is you count it by its pole. So this is index of South Pole. South Pole is equal to 1. And North Pole, the situation is the opposite. So you just this is called source of the vector field. This is the sink of the vector field. It just go into the vector field go into the North Pole, and then again as you rotate the 2 pi, so the vector field itself rotates clockwise, okay, 360 degrees. Okay, as you rotate, you have the vector field itself rotate 2 pi on the clockwise. So therefore, it's the same situation here, even though the direction of arrow is different. This is also rotate as you go around the anti-clockwise. So this is the opposite way of clockwise. Okay, anti-clockwise. If you rotate anti-clockwise, the vector field itself rotates 2 pi in anti-clockwise. So therefore, this is index of North Pole is equal to 1. Okay? And then, so people just write down sum of index of 0 of vector field x. So this vector field is called, so usually people call the vector field x instead of e over there. Index of 0 in this case is equal to 1 plus 1 is equal to 2. Okay? There's another way to so there are many ways to draw obtain the vector field on a sphere. Okay, sphere. There's another way of drawing the vector field is just you just start from North Pole and you just consider the following way. Anyway, and you just consider the following way. I'm not that good at drawing. So 0 of the vector field are only now North Pole. The last time, the previous example, 0 of the vector fields North and South Pole. Now 0 is only at the North Pole. South Pole is there is a vector field, non-zero vector field in South Pole, like this way. So the vector field is just draw along this line. It's called flow of the vector field. This line is called flow of the vector field. All this notion is now very primitive, and it's just in intuitive. That is the mathematics of 19th century, but the beginning of the let's see, that many people, great minds like Gauss, Riemann, Poincare, and so on, make this primitive notion into rigorous mathematics. That's what we are going to know. Anyway, so this flow, this is the flow, but the vector field is on this flow line. And then, if you look at the neighborhood of the, let's see, North Pole. So let me erase this one. So there's a North Pole, and there's a circle. You just draw a circle. And then, what you will see around here is let's see. I always make a mistake on this thing. So now, sorry. So here is like this way. Yeah. And now, so it's already inside. Let's see. Inside. So what's going to happen is you start with here, but at this point it's already tangential. Okay, so if you go to from this point and go to the pi over 2 or like a 90 degree, it becomes like tangential because the flow becomes like this way. So if you look at tangent, it becomes like this way, and then the flow at the end of the day. So if you reach this point, if you reach this point, it becomes inward, as you can see. So it becomes inward, right? So therefore, it becomes the flow is something like that, like this one. Okay. And then you can see the opposite way if you go around here. So at this point, it should become like also it should become like this. So okay, so that's the vector field look like near the North Pole. Okay, North Pole. Okay. And let's look at how many. So once you rotate anti-clockwise, how the vector field rotates. It starts with the go directed upwards, and already let's see, if you go here, it's already 180 degrees, and it's already 360 degrees, 2 pi, and then if you go around here, it's 3 pi, and this becomes 4 pi. Okay. So therefore, index as you go around the 360 degrees, so the vector field becomes 720 degrees. So therefore, index in this case of p is equal to 2. P is equal to 2. 2 times 2 pi. So that's the index. And this is the only zero of the vector field. Okay. So therefore, index in total index. Total number index is invariant. So, however you draw the vector field on a sphere, the index at the zero of the vector field, the total number index of the zero of the vector field becomes 2, which is the same as the Euler number. And so let's look at this example for torus. The vector field simply can write down like this way. It never vanishes. It never vanishes. Okay? There's no zero. So sum of index of course zero, because there is no zero of the vector field. Okay? So therefore, it's the same as here. Another way is you can mimic the same thing for using height function. Height function. Let me. So height function, if you start with torus and you just consider height function and draw the vector field, it's a bit tricky than the other example. For instance, height function, you start with this point and the top is this point. Okay, and there is something going on in the middle. So let's write down like this. And if you use this height function and gradient flow of the gradient flow of the gradient vector field of this height function, what's going to happen is as follows. So the vector field starts from here, and it's zero of the vector field, and it goes upwards. Now, however, so at this point, if you go around this point, it goes back. So it's hard to say, but so what I meant is now it's opposite side, and here is also. The opposite side also goes like this way. And at this point, it becomes zero of the vector field. It's a critical point of the height function. And from here, again, the vector field goes like this way, and the opposite way, like this way. So this is also another zero of the vector field. And again, the vector field goes upwards. And this is another point. So there's in total 4 critical points. This point, and this point, this point, and this point. Okay? And then let's look at so around this point is the same as here. Okay? At the upper point is also same as here. What's going to happen? But let's look at these 2 points. So then let's look at zoom into this point. Then vector field looks like the follows. So let's see. So on one way it goes to like a sink. On one way it becomes like a sink, but on the other way it becomes source. Okay? You understand? So then if you look at the neighborhood, it becomes like this way. Okay, so this is how it looked like around this. It's called around this point, zero of the vector field, and this is on the y-axis. Y-axis it becomes like a sink, and on x-axis it becomes source. Okay, so this is called saddle point. It's called saddle point. And then, if you look at how the vector field looks like once you go around the 2 pi, so it's more like a. So you start with this one, but now it goes to like this way. So you start this one, but as you go around, it becomes like this way, and this way, and this way, and then this way. Okay. So therefore, as you go counterclockwise, I'm not counterclockwise. Sorry, counterclockwise. My English is become poor. Sorry, counterclockwise. So the vector field itself becomes clockwise. Okay, clockwise. It's rotated clockwise. In 2 pi. So therefore, index of this center point is equal to what? Minus 1. Okay? Minus 1. Okay? The same thing happened here. This is the index is the same happening. One direction is look like a sink, a source. The other direction becomes sink. The same thing happens. So therefore, index is the bottom point, upper point is +1, +1, as we saw in the sphere example. But here you have a -1, -1, okay? In the middle 2 points, the saddle points. And if you sum them up, you get 0. The same as the characteristic of the torus. So So sum of 0 of a vector field index of x is equal to Euler characteristic. So this Euler characteristic is often write like chi. Yeah? So Euler characteristic chi. This is called Fokker-Hopf. So the first way, one approach to the Euler characteristic is V minus E plus F. This is the Euler characteristic. Another approach is just look at the vector field on the surface. So the other approach is the how many of you guys have taken the have already taken the general relativity? Can you GR course? Only very few. Okay. GR course. Okay. Okay. So we're going to introduce so-called curvature. So this is second way to approach the Euler characteristic. Third way to approach the Euler characteristic is as follows. You introduce so-called curvature. I mean, so in the case of surface, it's already Gauss already started the introduced notion of curvature. But the main notion of a curvature is introduced by Riemann or Gauss. Riemann. And also Christopher. In 19th century, the so-called you can introduce a metric on the surface. Physicists usually write the G mu nu, but I don't like the physicists just write G mu. This is metric, but this doesn't mean anything. You just introduce each point and some metrics which satisfy some certain property we will learn, and from here, so this is a metric which can measure. I mean, for you guys, maybe it's obvious, but there's 2 points. If you pick 2 points on the surface, you can consider the notion of the length between them. Once you introduce the metric, one can measure the distance between 2 points. So that's the notion of metric. But I mean, if you think it looks like very obvious, but this is very, very, very miraculous discovery by Gauss and Riemann. And So the Riemann tried to generate this notion in a higher dimensional manifold, so-called. So the metric, if you introduce a metric, so one can measure the distance between 2 points. Okay? For instance, so this is called Riemannian geometry. Another geometry we will learn is called the symplectic geometry. Symplectic geometry. Anyway, so let's talk about. Okay, that's the same. So this is Riemannian geometry. So we will learn symplectic geometry. In this geometry, you don't have a notion between distance, between two distant 2 points. So people just write down manifold M and omega. So this omega is called so-called two-fold, and it only measures this if you have surface, whatever surface sphere, it only measures the area. It's area of the region. So symplectic geometry only area matters. Riemannian geometry, one can introduce the notion of the distance of 2 points. But it looks like a ridiculous thing to consider. You cannot measure the 2 points between them. But in symplectic geometry, it's very the origin. It gives the mathematical foundation of classical geometry, so-called Hamilton-Jacobi and so on. Everything can be formed in terms of that language, symplectic geometry. That's what we're going to learn. So that's the detour of the. So this is the relation with classical mechanics. So here you have a Hamiltonian formalism. You have a Poisson bracket as you. You might have learned in classical geometry, or maybe you have learned F and G. Or maybe people just write X, E minus partial F partial E. So this is a Poisson bracket one can introduce in the phase space of classical geometry. You have learned in classical mechanics can be formulated in terms of the symplectic geometry. But so let's go back to the Riemannian geometry, where you can introduce the notion of the distance between 2 points. So one can introduce the so-called the curvature. The curvature. Or curvature. And from here, one can just go to a bit more primitive notion of the curvature, so-called Ricci scalar or so on. Anyway, so you just contract the indices, and what you get is a Ricci scalar or Ricci scalar curvature. And what Gauss has found, the metric